Hello again. Today I'm presenting the paper called Understanding Dimensional Collapse in Contrastive Self-Supervised Learning. Authors are from Facebook AI Research, including their chief AI scientist, Jan LeCun. The paper is from this year's ICLR, although I think the abstract, archive version was published last year. So it's a fairly theoretical paper. Experimental results just are done basically just to prove or confirm the theory. I took some notes. We'll go over everything. If you want to interrupt, ask a question or comment on anything, just do that. So in this paper, we are going to look at problems that arise in contrastive self-supervised learning, particularly what's called dimensional collapse. I'll explain some more details, but first let's follow the paper. Basically, a bit of introduction. Oh, there's some comment in the chat. Let me quickly look. Oh, okay. So we are going to look at contrastive learning as a self-supervised approach and its advantages. And in this paper, we will study when problems arise also for contrastive learning. Because the idea is that we want a representation learning algorithm that works without labeling, so it supervises itself. And the idea in contrastive learning is that we use negative examples, and we create them by positive and negative examples, and we create them by adding noise. At least in this paper, we add noise to the input vectors, and we study a special loss function that separates positive and negative examples, and we study the dynamics in the learning process. Okay, so there will be some math, mostly linear algebra, but nothing too bad. Okay. So there is one problem in self-supervised learning, because if we want to find the representations that make similar images similar, by the way, here we will only consider images. So all architectures are deep CNNs, and experiments are only image data. Okay. So the idea is that if we want to find the representations for images that are similar for similar images, it's very easy for models to collapse on a singular representation for all images. Obviously, that's useless, and hence there have been a number of methods to handle this problem. In this work, we will look at contrastive methods, hence the title Contrastive Learning, where we define positive and negative sample pairs, and we treat them separately in the loss function, and we will have a special loss function. There have been also non-contrastive methods which use, for example, clustering, or methods that minimize redundant information between the two branches. The branches are we have two branches here because one branch is the input image, the other branch is the image with added noise. I will see the diagrams in a moment. Okay, but there is this problem known as the dimensional collapse, because even if the whole solution does not collapse into the whole dimension, the whole representation does not collapse into fixed representation. Certain dimensions do. This has been observed and studied in the previous, again, very recent papers. But even if that doesn't happen, dimensional collapse is still present. Dimensional collapse basically means that the embeddings defined fit in a lower dimensional subspace, which means there is a lot of redundancy in the images, in the representations. Okay. So intuitively, this idea of adding negative samples should fix the problem, because if we add negative samples and we change our loss function to make the representations separate for negative samples, we should avoid even the dimensional collapse, because, well, we will end up with different embeddings. However, as we see in this paper, it's not necessarily true. So here we will show theoretical proofs for, obviously, for linear models, but also experiments confirming that for nonlinear deep models, which are actually in the appendix. Because with the nonlinearities, theory is not as straightforward. And it's actually quite common practice to study the linear case in deep learning settings, in terms of theory. Okay, so here we will show two different mechanisms that cause collapse. One is along the feature direction, where the variance caused by the data augmentation is less than the variance by the data distribution. And because in this, if that happens, we'll show in a theorem, we end up with a low rank matrix, the low rank covariance matrix, and that will cause dimensional collapse. The other case is if the covariance of the data augmentation has small magnitude. It's smaller magnitude than the variance along all dimensions. So again, this is a different theorem showing that there is another case when weights on certain dimensions collapse, because there is this implicit regularization happening by the model, because deep models, especially deep models, actually in this case only models with more than one layer, tend to find lower rank solutions. It's a regularization that comes with deep models. Okay, and based on these findings, they propose a simplified method called direct CLR, which is similar to the current state-of-the-art contrastive learning method, which uses this projection step. We'll look at that, which is a learned component of the architecture. So because we find out that actually, in theory, that learned component can be replaced by fixed diagonal low rank matrices, they actually do that and show that with this change, the models perform comparably well. Okay.
Vahan, I had a quick question.
Yes. So good time, actually. Yes, let's do it.
In terms of defining when there's dimensional collapse, the way that they said in the paper is that you calculate the embeddings for all of the whole validation set of the model you've trained, and then you calculate the covariance matrix based on those embeddings. And if my understanding was like, if that's lower rank, then the embedding space is lower rank. And I guess my question is like, why is that the case?
So that means so if the covariance matrix is low rank, then there is then there is linear dependency between the embeddings, right? Which is what creates the low rankness of the embedding space, because the vectors are linearly dependent. Am I right?
I mean, I don't know.
I think so.
Yeah, because if the vectors are linearly dependent, that means they span a low rank space. Basically, imagine you put all these embeddings under each other and create a very tall matrix, right?
So essentially, you could create a basis for the embedding space that was a fewer number of vectors than the number of dimensions in the.
Yes. So you can take that the whole matrix, do a singular value decomposition, and then end up with lower dimensional feature matrix, because obviously the feature dimension is much smaller than the dimension of vectors in the validation set. So low rank means you can do a PCA and reduce the dimension of the features of features. This is actually raises another question to me. So if you can do that for arbitrary size of features, can we iteratively reduce the feature dimension to 1?
Yeah, that would be complete collapse, right?
Yeah.
Oh, that they mentioned in the paper. Yeah.
Cool. Any other comments before we go to related work? Cool. Okay. So a bit of related work to prepare for the next section. So we will use this info NC loss function, which is a contrastive loss. We'll see the formula in a moment, but maybe I can scroll down. There's the loss function. Z's are the embedding vectors at the end of the neural network, so the logits, and Z primes are the primes means Z primes are the vectors after applying a random noise, and I's and J's represent positive and negative samples. So if you look here, so these two parts are the same, right? In the sum log, and then the numerator and one sum in the denominator are the same. But here we also have the negative example bits, which kind of regularizes to not allow complete collapse, right? Because I and J are supposed to be far. Okay. And yeah, there's the loss function we will study. The other important bits is, well, they also mentioned theoretical understanding of self-supervised learning, and basically say there hasn't been enough study. It's still somewhat mysterious and poorly understood. There are mentions of some works, especially the dynamics, studying the dynamics of the alignment of eigenspaces between the predictor and its input correlation matrix, and how they play a role preventing complete collapse. Right? So this main theoretical work in contrastive learning has been about studying and preventing dimensional collapse. And they also mentioned the implicit regularization part, that deep neural networks tend to find low rank solutions, which is sort of regularization, right? Because if you add an L1 norm regularizer, you are enforcing low rankness, which actually already happens with deep models. Okay. Cool. Let's talk a bit more about the dimensional collapse. As I said before, actually, let's look at the diagrams first. So we will talk about two branches in our model, and because we will have data augmentation, right? So there is an input x tilde, one branch goes up with the x, and then there is an encoder. So we use, in the experiments, we use ImageNet. In the and in the theory it's a linear model. Okay. So in experiments, we have a deep model with nonlinearities, residual connections, which actually are important. We'll see at the end. But theory is done on linear models, one layer or two layer linear models. And then anyway, then this encoder gives us an embedding vector, which then pass into the loss function we just saw. Basically, those z and z primes are the outputs from the two branches. Okay, and then we use the loss function. Now, when we talk about collapse, they made a nice diagram here showing that if you have two similar representations, they collapse into one point. But even if that doesn't happen, often we have what's called dimensional collapse, when we end up having all representations in a lower dimension, representable in all lower dimension. So even if you have a 3D sphere here, in reality, all our representations are on one circle, right? So that's the lower dimensional bit. Cool. They also show an example of how the singular values drop to zero fairly quickly, right? So the first few are okay, are non-zero. Those are in log scale, by the way.
Can I ask a question?
Yeah, of course.
I was wondering if you make the embedding space that you're planning to fill smaller, would you still observe that? So is it say if I give it less space, it would still fill out only a subspace, or is it like if I make it just small enough, it just fills the dimensions, whatever, to the space it has?
I was wondering the same thing. In theory, in the theorems, there was nothing to suggest otherwise. There was no lower bound on, at least I didn't see lower bound on the embeddings, which is why I said the earlier comment, right? So does it mean even if you start with high dimension, if it drops, can we change our model representation to lower dimension and end up with one dimensional, with a matrix of rank 1, right? Yeah. I think that's what would happen, right? No matter how small your embedding is. So experiments are 128. Wow.
Because it's funny, right? You would have thought that somehow this training finds something in the data, right? That the data is actually on some lower dimensional space. But now this seems to suggest, right, that actually it might be even something else here going on. Right.
So in the theory, I will actually go through the theory a little bit to show that, because when you have, for example, when you have two layers, they show that the two orthogonal matrices after SVD decomposition on each layer, the multiplication ends up with a diagonal matrix. So kind of the two singular, the two orthogonal vectors, singular vectors, collapse to each other. That's the training, because of training, right? Because of the linearity of the model.
Yeah.
So I guess whatever feature dimension, there is nothing about feature dimension there. It's about the two vectors becoming orthogonal and low rank.
Yeah. Well, that's cool. Oh, interesting. Yeah.
Yeah, it's very interesting. Okay. Any more questions before we do a bit of math? Singular value decomposition, that's the main thing we will use. Actually, let's define this C matrix. So C is the covariance matrix, the one that Peter mentioned earlier. Dimensions are, no, this is the covariance matrix at the end on the last layer, right? So covariance matrix defined by the Z's. Okay, so these are not this is not a covariance between all embeddings created on the validation set. Those are done with the Z vectors. Okay, from the output of the model. And we will do a SVD decomposition. So the important thing here is that if you're not familiar, it's like a eigenvalue decomposition. U and V are orthogonal, S is diagonal and contains the singular values. It's basically an extension from eigenvalue decomposition, except here matrix doesn't have to be a square, although in this case it is square. Okay. It will also use the concept of positive definiteness, which means all singular values are positive. Okay. Okay, so if you go further, first we studied remember at the beginning I mentioned two cases for dimensional collapse, right? Here we are going to study the dimensional collapse caused by strong augmentation. Strong augmentation means when we create these two branches, they are too different. Okay, the inputs become too different. So here we are going to look a very simple one-layer linear model. W are the weights, inputs are X, and then we end up with a Z, with a linear model here. And we will use the same contrastive loss with positive and negative examples. Okay. And they also mentioned that, I don't know if it's very important here, but they mentioned that the negative distance between Z high and Z high prime can be replaced by their inner product if you normalize them. Fine, right? And they use the basic stochastic gradient descent without momentum or weight decay, which is what they do in all everywhere for theory. So it doesn't matter too much, right? Either in terms of theory. Okay, so I had to go look at the appendix to write some clarifications for the lemmas here. Basically, first, we are going to study the dynamics of the weight matrix. Okay? Dynamics means the gradient over time. Okay, and we show that it is the negative G matrix, which is a sum of gradients over Z i's and Z I primes multiplied by their corresponding inputs. Okay, it's just a result we will use later, but the proof is actually very straightforward. It's basically just taking the contrastive loss, doing the gradient, and applying chain rule. Basically, we want a calculation for the dynamics of the weight matrix. Okay, they use this definition that the dynamics is the negative gradient of loss over W, and then apply the chain rule. Okay, I should be fine. And then they define this X matrix. This looks long, but basically we have these alphas, which are coefficients, and the X, same Xi, Xj, positive, negative. So examples with augmentations. And we need this X matrix because that's the one that defines the dynamics. So we find that G, the matrix up here, defining the dynamic of W is negative W times X. So this is the X that gets multiplied by W each iteration. Right? That's the one that defines how the weight matrix changes as the model is trained.
Isn't it G? Oh, G is the change in the weight matrix.
Yes.
Yeah. Yeah. Okay. Cool. Got it.
Okay. Now the next lemma says that this X matrix, which defines the dynamics, is a difference of two positive semi-definite matrices. Okay, so which are those two sigma 0, sigma 1s, which are defined with those alpha coefficients and the differences in X. Again, no need to study the proof, but it's important that it's a difference of two positive semi-definite matrices, because as we see later, this difference can cause either a low rank, can cause a low rank matrix if no, not low rank, can cause a negative definite matrix for X. Okay, and that will define the collapse. So because of this formula, the amplitude of augmentation determines, augmentation is the difference between xi and xj. The determination defines whether X is a positive definite matrix. Okay, so if the augmentation is too large, X becomes is not positive definite. I think it becomes negative definite, right? And that can be a problem.
But when we see how the evolution happens, right? So it's proportional to X. Does the positive definiteness then mean that the W shrink, the weight shrink indefinitely, or?
No, I think a positive definite means there are no zero singular values, right? Because it's not semi-definite, it's positive definite.
Yeah.
And that means there is no collapse.
But wouldn't it, on the other side, mean it would be an explosion of values, right? Because it's roughly W, the derivative of W is proportional to X times W itself, right? So if you were to reduce it down to one dimension, isn't it, if X dot is proportional to X, then X or Y dot is proportional to Y, then we would expect this to become bigger and bigger and bigger. On the other side,
I didn't get that out.
But if you plug this G value into the equation for W dot.
Yeah, from here.
Yeah. So W dot equals minus G, and that of course then means it's W dot is proportional to X times W itself, right? Now let's assume there is like one dimension in which X is positive definite, right? So we must have some kind of sub space in there where we have.
What do you mean dimension where it's positive definite? You mean it has a positive singular value?
Yeah. So it has a positive eigenvalue, right? Then you would think that along this axis, W. So at each point, this weight is sort of projected onto this axis. And is essentially growing, right? Because it's growing indefinitely. Would you expect then that this space where we have a positive definite or a positive eigenvalue, it would essentially grow, whereas if you have a negative eigenvalue, it would essentially shrink.
Interesting. You mean as we train?
Sorry, I was just going to say it does shrink. It does shrink because they do say when X does have negative eigenvalues, then the weight matrix W has vanishing singular values. So that does happen. I'm not sure about what happens in the case when X is positive definite. I guess everything explodes, but maybe it approaches
probably should always normalize.
Yeah, right? Well, to normalize it, it should be fine, right? But when you normalize, you would expect that all those vectors that have where the X has the same magnitude should become roughly the same in size. Isn't there something like essentially the more you apply it, the more the largest eigenvalue is filtered out, so that you essentially also have some sort of collapse again into a single space? I'm not sure.
But that's what I want to show, right? That there is a collapse.
Yeah, I'm just saying how is there possible? how is there possibly a way for W to be a constant output rather than anything that is either infinite or zero? Oh, that might be just because it's a linear approximation, right? Because we at any point in time W is only allowed to change very little and until X changes again. So that might be where this sort of breaks down this thinking.
I'm not sure, but
the X is X a constant matrix, or does X change slowly as you change the training? It's a constant, right?
X's are constant. Yeah, it is.
No, it's X is based on the X's are constant, but the alphas or A's, whatever that letter is, they change with as the embedding space changes, and since this is gradient flow, it changes like constantly.
Yeah, but you would sort of expect that for a short period of time, probably the alpha is relatively constant, but then over time it slowly shifts sort of adiabatically. Yeah.
So alpha sum up to 1 over J, but they can change, because so are the softmax of similarity between Zi and Zj.
And that's
no, I didn't. No, sorry.
So no, go ahead.
It's a tangent. So I'll if you have something to say about this, then I'll wait.
Go on your tangent, please.
Okay. I actually haven't. Last time I worked with contrastive losses was like 2-3 years ago, and back then, maybe 3 years ago. Anyway, the contrastive loss was much simpler. It was literally just like the square difference between the positive examples minus the square difference between the negative examples. So like the L2 norm of the two.
Mm-hmm.
And now it seems like the state of the art is using this like a softmax within the function.
Yep.
Which I hadn't seen before today. So I was thinking to myself, I wonder, I mean, I didn't read info nice or whatever it's called, but I'm wondering what prompted this to be considered better and why softmax. But anyway,
softmax is always good. I mean, I haven't read the paper like this. There is a reference 2018, but maybe we can read the original paper. But yeah, that seems to be the state of the art.
Yeah, it's so the insight of the actually probably not a bad idea to think about how the loss itself behaves in the extremes, right? So if there's a collapse, then the log goes.
So
no. Oh, no, the log becomes very, very small, right? Because essentially the log goes as 1 over the number of data points you have, because So say if all the z's are equally distant, right? So then the log goes as 1 over the sum of data points. Right?
What was the first part?
If all the zi minus zi prime are equal distance from the z, have the same value as zi minus zj, right? Then each exponential becomes.
Why it shouldn't be, because those are augmentations. Those are examples.
Just trying to think what are the limiting cases, right? So in that limit where essentially the noise is strong enough that the difference between the augmented and the non-augmented are on average the same, right? So you get 1 over n inside the log. And so log 1 over n goes to, so the loss becomes essentially log n, the number of data points you have, right? That's already interesting, right? Because typically you would expect something that goes to a constant, right?
So more points, data points increase the loss.
Yeah, I would think so, but unless I'm making a mistake here. I don't know.
Interesting.
Sorry, please go on.
Yeah, there is a lot to actually discuss here, because it's also a relatively new topic for Paper Club. So yeah, we can talk more about this. But let's finish it first, and then we can have more conversation. Right. So then, there is a assumption with fixed matrix X, right? There's also some assumption for the first theorem, and strong augmentation such that X has negative eigenvalues, right? The weight matrix W has vanishing singular values. Okay, not all singular values, but some are vanishing, which cause the dimensional collapse for the outputs. Okay, with strong augmentation and the embedding space covariance matrix becomes low rank, but that's a direct consequence of the theorem. Okay, so as you said, X may not be fixed, but that's an assumption for the theorem. I think we can. What they say is in practice, you may end up with block diagonal covariance matrix instead of a diagonal one, because X may not be fixed, I think.
Wait, no, this is generating the underlying data. It says, isn't it? It's saying we set the augmentation as additive Gaussian with a covariance matrix that's block diagonal.
Yeah. Okay, so maybe I jumped a bit too far because there is discussion about it later, but we'll get to it later. Thanks, Peter. Okay. A bit of study about how singular values drop.
Could I ask a quick question here?
Yes.
Just so my understanding of this plot is that they take the singular values and they rank them, and that's what the x-axis is. So the 0 is like the largest singular value, and whatever 15 is the lowest. And then the fact that you have this big drop, that indicates that, I mean, they're not 0 singular values. I don't know, but they're diminishing, which means that essentially that it's like they're 0.
But they're not as low. 0.2 and 1 are not that different, right?
But isn't that wouldn't it have to be that you have like, if the idea is that dimensional collapse means that you have singular values that are very close to 0. And if they're not close relatively, what do you mean by relatively?
If the largest one was 1,000 and the small one was 0.2, you could say that there is collapse. But I wouldn't say that if it's between 1 and 0.2, I wouldn't call it a collapse, right? Because the difference is only 10 times. Because it matters, because you can always multiply eigenvalues by a constant, right? So what matters is the relative change. But I think what they want to say is that there is a drop, and they also study what's K here, how it changes various augmentation amplitude K. Depending. Okay, so what they're actually studying here is that they want to see how much extra augmentation affects the collapses in singular values. So what they are showing is that higher K, which means more augmentation, causes more collapse. Because if you look up here, like, low K means, well, there is no change really.
But this is interesting, right? Because it just shows the magnitude of the collapse essentially changes, but not the index at which it changes, right? So the index seems to be independent of the methods being used.
Yeah, that's cool. Yeah. In this one specific case, because it's a toy example, I think. But still, yeah.
Oh yeah.
I think the index is dependent on the block diagonal covariance matrix. Sort of how much of the augmentation you're actually adding, which is I thought was pretty interesting.
Yeah. You mean this 8 is related to this 8?
So almost certainly, right?
Yeah.
Yeah, it is. Yeah.
Yep. Okay, we have still one more chapter to cover. We'll be quick. So here we will look at the on the case when there is no strong augmentation. So the previous case does not hold. So the X matrix remains positive definite. However, we will look at the overparameterized deep models and considering that they have implicit regularization causing low rank solutions, and study their behavior here and understand why there is still dimensional collapse. So here we have a 2-layer linear model. So instead of having a deep model, in theory, we do 2-layer model, which means actually we have 2 weight matrices. We will have dynamics for both of them, similar lemma as before for both of them. And the G is defined with the product of the 2 weight matrices. Okay, this is important because we will study the product of the 2 weight matrices and how it evolves. And here we also assume that the X is positive definite. Okay. Right. So we look at the as we did decompositions for both W1, W2, and because if you do that, this product becomes the orthogonal matrix, diagonal matrix, and then we studied the product of the right orthogonal matrix of W1 and the left orthogonal matrix of W2. Because if you put them in here, that's what we get. And the theorem that we get says we end up with a product that tends to a diagonal matrix as training tends to infinity. So this is what causes the collapse. Also, tells us how to improve the existing self-supervised learning models. Proof is in the appendix. We are not going to go through that.
I have a quick question,
Yes.
which may be a silly question, but I was thinking their model is 2 weight matrices with no nonlinearity between it. So you could express the 2 weight matrices as a single weight matrix by just multiplying by each other first. And then I'm wondering why the logic of the previous proof doesn't hold. Like,
no, you can't really do that because then it's a different model, because now we have 2 matrices changing almost independently, not independently, but separately.
Yeah.
It's about the representation of the matrix.
Yeah, is exactly how these update by themselves.
Yeah.
Yeah.
They're not independent, but we want to look at the decomposition and then study how these orthogonal matrices update and how they become their product collapses to an identity matrix.
Because the gradients are not independent, right? That's the
yeah. You can also see that assuming that the product of the 2 is not 0 and X is positive definite, which is not the case for the previous setting, right? We have distinctive singular values. Then the alignment matrix tends to infinity. Here they also show that actually in practice, not all of this may hold, or assumptions may not hold, but even if they don't, we will end up with converging to a block diagonal matrix instead of a identity matrix here. And there is one example demonstrating that. Okay. And then there is another theorem saying that if the two weight matrices are aligned, so that the two orthogonal, well, the two or the right orthogonal matrix of the second and the left of the first weight matrix are equal, then the singular values of the weight matrices under the info-nice laws evolve by these formulas. So now these are the gradients of the singular values, right? Again, proof is in the appendix, but this uses some linear algebra, saying that if the matrices evolve according to certain rules, we can derive also the singular values evolve, how the singular values evolve. Now here, the important thing is that we can show that the dynamics of the first singular values can be given also using by it's given with this cross formula, right? Because we can replace the sigma 2 here with this formula that I highlighted, okay, for both cases. So this helps because because we end up with a closed form formula, and then we notice that the X is a positive definite matrix. If it's positive definite, then this multiple the product is also non-negative, right? And then that will help us define the sigmas. Okay, and then because of that, we can end up with this corollary, which basically says that it says with small augmentation and over-parameterized linear networks, which are the assumptions here, the embedding space covariance matrix becomes low rank, right? And that's the important result here. Yes.
A quick question: when they generate these plots, yeah, yeah, when they generate these plots, they simulated some data, right? And they simulated also the dimensionality of that data to be effectively lower dimensional, right? There was this block matrix, no?
Yeah.
What would happen if? Yeah, but what would happen if that one is strongly asymmetric in the sense that there's one dimension in that data set that would be larger than the other? So essentially you have an unnormalized data set. I think then I would feel that this always will go towards a single dimension only, no?
I think they mentioned that either in the appendix or somewhere here. Yes, because in these experiments, they make sure that the assumptions hold, which is not true in reality, right? In which case, you will end up with a block diagonal matrix, actually.
So even if X has eigenvalues that are of very different sizes, essentially. Because usually you would expect if you apply something over and over and over again, that you sort of filter out something. I think this is, for example, how many numerical schemes work, right? You apply a matrix product over and over again, and at the end, if you do it often enough, essentially you have the largest eigenvalue left. And I would have expected something similar happening here, but my intuition might be just very wrong.
No, they do mention that. I'm just trying to remember where it was. I think maybe it was in the appendix. Let me maybe find here. So here they talk about more layers on linearity. But they do mention that because it depends on the initialization of the weights, right? Is it what you're saying?
And the weights or the training set, right? So the X is made up of your data, information about your data, right?
Mhm.
And so whether that one is a well-balanced data set where all dimensions are roughly equally populated, or whether there is some dimensions that have just much more variance than others. So essentially you didn't normalize your data set before putting it into your algorithm. Like
Mm.
that
Yeah, maybe you should normalize it. I know they don't mention that. No, I thought you
Yeah.
meant about the weights, but I don't know. I didn't see anything about the data set. So those are all toy data sets, right? They are prepared for the example to verify the theory.
Yeah, and I think there they essentially set the variance of all dimensions to be equal.
Yeah, exactly. Yeah. There are some real life examples later. Maybe that helps. Also, okay, let's quickly look here. Maybe it will answer the question, Arvid, because there is an interesting observation here, I think. Okay, so knowing what we know, they propose to change the existing contrastive learning state-of-the-art methods to a more simple version. But let's quickly see what the current versions do. So basically, you have an encoder, which gives a representation. But then there is this projector part, which is a learned model with its own weights. But those are usually 1-2 layer small models that generate the embeddings. And as has been shown in recent papers, this projection bit is actually very important. Now, what they're proposing is, since we know that the product of the two singular values is actually identity and low rank, so both of them, right? So I try to draw here a diagonal low rank matrix here. So they're proposing to replace the projector with a fixed matrix, right? If you look here, basically, instead of having this projector step, add the z's on top of the representation, which is what the low rank identity matrix, low rank diagonal matrix would do. If you multiply with that, okay? So that's the simplified version here. And a few experimental results. So depending on the, which they don't actually mention in the text, but depending on the depth of the projector, if it's only one layer, then our direct method is actually even slightly better. So this was tested on ImageNet. But if you have a deeper projector, the performance is actually much higher, right? So maybe that's because in real life, those assumptions that we saw for the theory that also Arvid mentioned, maybe that's also a limitation, right? And we need a more sophisticated projectors here to handle that.
I think these results are why this paper didn't get like a best paper or honorable mention, because it's like, the theory is cool and it makes sense, but then the experiments don't validate that it's like super applicable.
Yeah, because yes, exactly. So maybe there is follow-up for the to do something to handle more complicated settings, which the two-layer projector can do, apparently, right? Some more. These are some more studies, ablation studies, I think, but not very useful. It just basically shows how the singular values drop. Now, notice that here, the y is in log scale, right? So minus 20 here, but then they drop at some point. Again, validating that there is collapse. Except, yeah, no, it's fine, just that. And then they also mentioned that it's residual connections in the deep embedding method. They use a convolutional block, but the deep convolutional architecture here with residual connections. And then they're arguing that residual connections make sure that this whole thing makes sense, because otherwise, if you have low rank here, you will keep the low rank going, right? Same for the forward pass.
Here, I was wondering, why didn't they just randomly select the low, like the dimensions from the representation? You know, like why did they fix it to the first D not?
D is a hyperparameter.
I know, but
this, yeah.
But they could have said like we assume that the lower rank of this is 5, and you have a 128 dimensional vector. Why not randomly continuously select 5?
You will randomly select 5 of them, not the fixed. I don't know. Good idea.
Because I was thinking maybe this would could even force it to be higher dimensional or something like that. I don't know, but anyway. But I'm sure that the authors thought of this, so it means that this result, like there was either no improvement in performance or it was worse. But it was something I was wondering, like, why not just randomly select the dimensions?
Yeah, good point. I don't know why not, but yeah. Right, so they do a bit of a ablation study to verify their propositions. Right? They're saying since the first 2 are similar, then it verifies proposition 1, and second 2 also verify the proposition 1, and then because the last 2 are the best, which are the new method, they verify the last theorem. I think that's all. Try to go through the appendix also. Yeah, they do also a quick experiment with a nonlinear deep model to show that even though there is no theory in practice, the singular value still collapse. With more layers, they collapse more actually. 1 layer, they don't collapse, as also confirmed by their theory. You need more than 1 layers. Okay. Any last comments? Okay, this was quick. Okay, so I'm going to stop recording.